Hello students, welcome back to this course on aromaticity. In the previous module, we discussed about the types of aromatic compounds and we emphasized the concept of Huckel, and we applied Huckel's rule to various systems, and we specifically studied about the planar systems that obeys Huckel's rule. Later, we also studied about the Mobius aromaticity, which was exhibited by non-planar systems, where we understood that if a system has a 4n pi electron, then it would be aromatic, and if it has 4n plus 2 pi electron, it would be anti-aromatic as far as Mobius system is concerned. But in 1959, Saul Winstein talked about a new class of aromatic molecules during his study of tris homocyclopropenyl cation. And these molecules were termed as homoaromatic molecules, which showed discontinuity in p orbital overlap. We have understood in our earlier systems that for a molecule to be aromatic, there should be a continuous overlap of p orbital that enables the molecule to have a complete delocalization, which provides an extra stability to the molecule and which adds up to the resonance energy of the molecule, and thereby the molecule becomes aromatic. Whereas in the homoaromatic systems, there is a discontinuity in the p orbital overlap due to the presence of single sp3 hybridized atom. So we can say that those compounds where the stable configuration system with 4n plus 2 pi electron can only be formed by bypassing one saturated sp3 hybridized carbon, which leads to homoaromaticity. Please remember, such compounds are definitely less stable than the aromatic compounds which has a complete delocalization, as they show a poor overlap of p orbitals. The best example would be our cyclooctatetraene system. Cyclooctatetraene system, which is first when it is treated with concentrated sulfuric acid. So this concentrated sulfuric acid can react with this cyclooctatetraene system, which leads to the formation of a homotropylium ion. Now this homotropylium ion can be represented like this, and you can see here the delocalization of p orbital occurs by bypassing one sp3 hybridized, by bypassing one sp3 hybridized system. So you can obviously see here the 6 pi electron assumed to be delocalized over 7 carbon atoms, and the 8th saturated atom undergo a non-planarity. So these type of homoaromatic system can exist as cationic and anionic species, but some studies also give evidence for the existence of neutral homoaromatic molecules, but they are less common. So the best example would be homotropylium cation, which is C8H9 plus, is the best studied example, and if we add up a CH2 group, it becomes a homotropylium ion. So tropylium ion with the addition of CH2 becomes a homotropylium ion, and with an addition of one more CH2, it becomes 1,3 bis homotropylium ion. Now what are the evidences for this homoaromaticity? Winstein proposed the first evidence for the homoaromaticity, where it took tris homocyclopropenyl cation, tris homocyclopropenyl cation, which is 3, and this is formed due to the removal of a tosyl group from this particular system. The evidence was collected from the acetylysis experiment of 1. So this is 1 when R is equal to H, where cis epimer reacts 35 times faster than the trans epimer. Now, evidences for homoaromatic structure was acquired from deuterium scrambling. When R is replaced with deuterium, it was found that 66% of deuterium was found on cyclopropane. So you have a this is actually a bicyclic system where you have a cyclopropane system attached to a another 1, 2, 3. Okay, a 3-member, maybe a 5-membered. Okay, so we can call it as a 5-membered ring. Okay, so it was found that 66% of deuterium was found on cyclopropane ring system at position 1. You can see position 1 here and position 5 here, and only 33% on carbinol carbon. Okay, that is at position 3. So this is the carbinol carbon at position 3. This suggests that all the 3 positions, that is 1, 3 and 5. Okay, so all the 3 positions 1, 3 and 5 were equivalent. So this equivalency arises because of the delocalization of pi electron, and therefore the structure 3 was later called as homoaromatic. Okay, so this is one of the best evidence, and after this discovery many cationic, neutral and anionic compounds have been suggested to show homoaromaticity, and these compounds are stabilized due to homoconjugation. Now, what is homoconjugation? It is, in other words, it is homoconjugative interaction accounts for the complete cyclic delocalization of foreign electrons and lowering of energy. But there are also other conditions which are responsible for the characteristic aromatic property of these compounds. Let us see what are the conditions that are laid for a molecule to be homoaromatic in nature. So the criteria for homoaromaticity, the first criteria is the molecule should possess one or more homoconjugative interaction. In other words, there should be a cyclic delocalization bypassing one sp3 hybridized carbon. So it should be either through bond or through space closing cyclic conjugation. Then a closed cyclic system must show electron delocalization through effective overlap between the pi orbitals of the cyclic system, and the bond orders and pi character indices should be close to that of aromatic pi system. Positive and or negative charges should be delocalized throughout the cyclic system in case of charged molecule, and there should be a large degree of bond equalization. In other words, the bond lengths should be of equal length, resulting in difference of bond lengths from those of normal single or double bond. So there should be an equal bond length between all the carbons. For either cyclopropyl or non-bonding homoaromatic systems, the number of pi electrons participating in cyclic electron delocalization should be close to 4n plus 2, and homoaromaticity should have a resonance energy greater than 2 kilocalories per mole, which leads to stabilization. And there are significant equalization of C13 chemical shifts in the cyclic system. So no bond homoaromatic system should possess exceptional magnetic properties that should lead to a significant chemical shift. That is, it should not have the normal C13 carbon chemical shift. It should have an aromatic C13 chemical shift. And the magnetic susceptibility adopting a maximum value for an unconstrained homoaromatic system, indicating homoaromatic electron delocalization, and a large chemical shift difference between the exo and endo protons when the molecule possesses a CH2 group properly located above the ring. So these are the criteria for homoaromaticity. Let us move on to our next topic, that is aromaticity in fused ring systems. Now, as far as aromaticity in fused ring system is concerned, we have seen such fused ring systems in our earlier discussion. So, the criteria for aromaticity in monocyclic hydrocarbons can also be applied to the what you call the cyclic hydrocarbons that has polycyclic systems. So these are some of the well-known examples which we have seen in our earlier classes. For example, naphthalene, which has 10 pi electrons, 4n plus 2 system. We have phenanthrene and we have chrysene. Now, in all these systems, as the number of aromatic ring increases, the resonance energy per pi electron decreases. Then what happens to this? As a result, larger polynuclear hydrocarbons have a tendency to undergo reaction to an internal ring to give more stable compounds. For example, if we take an anthracene, so anthracene has the tendency to undergo addition reaction in the internal ring, which gives more stable compounds. So you can have a mixture of cis and trans isomers. So as a thumb rule, we should remember that as the number of rings increases, the resonance energy per pi electron decreases, thereby making such molecules susceptible for addition reaction. Another class of compound which can exhibit aromaticity is azulene. Azulene is a non-benzenoid system and it has a significant aromatic stabilization. It has a noticeable dipole moment of 0.8 dBi units, which makes it polar. It is a combination of cyclopentadienyl anion and cycloheptatrienyl cation. In contrast, when we talk about pentylene and eptylene, which possess fused 5 and 7 membered ring respectively, are not stable as expected on the grounds of anti-aromaticity. So when we look into this system of azulene, so when we see azulene, you can see it could be observed as a combination of a 5 membered ring and a 7 membered ring. When you look into a normal pentylene, it is highly unstable and it readily dimerizes. So azulene can be looked as a combination of cyclopentadienyl anion and cycloheptatrienyl cation. Similarly, in eptylene, you can have a cationic system that results in the delocalization of pi electron. Now, all these systems are non-benzenoid systems which can exhibit aromaticity, and they are also polar and they exhibit a considerable amount of dipole moment. So these are the examples for azulenes. Another class of compound that exhibit aromaticity are called fulvalene. They represent another interesting class of compound which can have potential aromaticity. So a fulvalene is a cyclic system, two cyclic rings attached with a double bond. So among possible symmetrical structures, we have triafulvalene, pentafulvalene and heptafulvalene have been prepared and but were found to exhibit a polyene character. They are not aromatic unless and until they become polar. However, when a combination of rings such as cyclopentadiene and cyclopropene were examined, so you can see a combination of cyclopentadiene and cyclopropene, results were in the support of existence of resonating structure. So this fulvalene can exist in these resonating forms where this becomes a cyclopentadienyl anion and this becomes a cyclopropenyl cation. So there is evidence for the large measured dipole moments of phenyl substituent analog X and a reduced barrier of rotation as revealed by NMR of the dialkyl. So if you have large substituents, there is a potential reduction in the rotation of this bond. That once it becomes a single bond, there is a potential reduction in the rotation of bond, thereby its planarity is preserved. So when there is a there is a reduced barrier of rotation which is revealed by NMR of the dialkyl substituted analog of X are manifested of such effects. So this is one such example for a fulvalene. So azulenes and fulvalenes are another class of non-benzenoid systems that exhibit aromatic character when the rings themselves become cation and anion that favors the delocalization of electrons. So I would request you to study more, refer more. I will share this also, so you can refer more and you can understand the aromaticity in non-benzenoid systems. Thank you.